Welcome to Lecture 10, Analyzing Starlight. Today we'll begin the first of several lectures dedicated to analyzing starlight and finally beginning to ask the detailed question, how do we squeeze as much information as possible out of the light that we gather? Because as I've mentioned on a number of occasions now, basically what astronomy is the study of light. Because with a few exceptions, we're stuck here on Earth and we get the light that comes to us from the cosmos. The goal is to learn about the cosmos by analyzing that light. Now that we've spent a number of lectures learning about the properties of light itself, and then in Lecture 9, the way that we gather that light using telescopes and spectrographs, for example, to split it up. Today, we're finally going to take the first baby step, if you will, into the second third of the course, which is dedicated toward actually assessing the things that are out there, learning about stars by virtue of their light, and so on. So let's dive in. Stars. We know what a star is. It's a ball of burning plasma fueling itself through nuclear fusion processes in the core. And we'll learn a lot more about that in detail. But almost everything that we see in the night sky is starlight, either directly or indirectly. For example, the moon doesn't send us moonlight, right? It sends us starlight, just reflects the sun's light back towards us. So almost everything that an astronomer does is somehow related to starlight. Now, when we look up, there are a few different things that we can see. We see individual stars, if they're close enough, but for larger objects like galaxies, which are extraordinarily far away in general, we're certainly with our naked eye, and often not even with telescopes, are we able to distinguish between the different stars in huge clusters of stars, including and up to galaxies and galaxy clusters. So the closer something is, the easier it is to resolve. The farther away, the harder it is to resolve. But when we look up at galaxies, what we're seeing in a picture like this, for example, is the light from billions of stars all adding up to make, an amorphous glow. So, as we talked in some detail last time, there's a concept of angular resolution, and we can ask the question, are we able to resolve two objects? And that's a function both of the aperture of our visualizing device, whether it's our eye or a telescope, and a function of how far away it is. These galaxies are so far away that with anything but the very best technology, and even then it would require a relatively close nearby galaxy, these billions of stars are mostly going to combine into just a generic glow. When you look at this image, you do see some isolated dots of light, but it's very difficult to tell whether that's an individual star that is particularly bright, or if it's a star cluster full of thousands of stars, for example. It's from a distance you really cannot tell. So when it comes to galaxies, what we know quite a bit, and we will near the end of the course actually start talking about galaxies themselves. But as I mentioned already, they're collections of billions of stars, and the one that we know the best is the Milky Way because we happen to live inside it. And there are pros and cons of that. The good news is that we have an insider's view of the Milky Way. On the other hand, it also means that we can't look at it from above, for example. We can't get outside it because it's so huge. And so again, there are pros and cons of that, but it is what it is, and so we work with it. Our galaxy is shaped like a spiral, and in particular, it's known as a barred spiral galaxy. And again, we'll say more about that later in the course when we talk about classifying galaxies. And while we can't take a picture of the Milky Way from above, we know basically what it looks like, and it looks something like this. It's a spiral because it's a spiral, again, the name thing. And it's called a barred spiral because there's a small bar that goes through the center of the galaxy. Some barred spiral galaxies have larger bars, some have smaller bars. The Milky Way's is relatively small. It's not particularly prominent, but there is a bar there, and so it's called a barred spiral. If you were to look at an edge-on view of the Milky Way, it looks something like this at right. So it's very flat relative to its total size, and the vast majority of the stars lie in the galactic plane. So when we were talking about the formation of the solar system, which we didn't go into a lot of detail, but I did allude to, I talked a little bit about how the solar system formed out of a cloud of gas, and as gravity initiated the collapse of that cloud, it began to rotate, and because as it rotated, it tends to flatten out. And the same is true on a much larger scale when it comes to the galaxy. And so, as a result, a lot of things in the universe are largely planar. So, galaxies are largely planar, solar systems are largely planar, and this is why. So, but there are exceptions. You can see, despite the fact that the vast majority of the stars are here in the galactic plane, including a number in the central bulge, you do have stars outside of that plane as well, and we will talk about that in a lot more detail again when we start focusing near the end of the course on galaxy formation itself. But for right now, it's good to know at least have a bird's eye view, if you will, of what our galaxy looks like. The precise number of stars is, as you might imagine, hard to pin down in detail. And so right here it says 100 billion stars. You may see up to 200 billion in estimates. When it comes to counting things like this, as I said, it's hard to take a detailed census of the numbers of stars, because we know what we can see, we don't know what we don't see, right? We can estimate it. So we know that there are 500 billion stars in the Milky Way, and we know that there are more than 50 billion. But so 100 billion is a good estimate. So stars come in a number of different flavors, and by which I mean colors. So there are red stars, there are blue stars, there are white stars, and we'll talk about those in detail in the coming lectures. But in addition to different colors, they come in different brightnesses too, and those are related, and they're both related to temperature. So if you look at the constellation Orion, for example, with Orion's belt here in these three central stars, you can see there are a lot of blue stars here, or at least it's how they appear here, and then there's a very noticeable red or orangish star up here. This, for what it's worth, is the star Betelgeuse, which is a red giant. It's actually been in the news somewhat recently because there was some speculation that it might supernova or explode. It hasn't done that yet, or at least we haven't seen the light from that yet. It is over 600 light years away, so we wouldn't know for a while. But you can already see just in this image that there's some noticeable variation in the colors and brightness of stars. And as we've talked about before, from our vantage point, we may look up and we see one very bright star and one very dim star, but it may just be that what looks bright to us is just a star that's very close, and what looks dim to us is just very far away. So there's this connection that we'll revisit today between brightness and distance and luminosity. So I kind of answered my own question there, but it's important to keep in mind, just because a star appears brighter doesn't mean that it is more luminous, right? It could be very luminous, or it could just be very close. And one of the things that we're going to be thinking about as we start to analyze starlight and learn about the techniques that we can employ to do that is to figure out how can we extract this information, how can we separate out the effects of distance from the effects of luminosity, and with the goal of actually figuring out what is this star really like, how massive is it, how hot is it, how close is it, rather than just some combination of those factors. So to state, what might be obvious, even a very bright light, a very bright star, or a bright flashlight can appear dim if you're very far away from it, right? So how do we tell if a star is truly brighter than its neighbor, or if it just happens to be much closer to us? And the answer is something that we do take for granted, that we use every day without thinking about it, and it's a concept known as stereoscopic vision, which is a fancy way of saying we're going to view the same thing from two different places, and we're going to look at the relative movement of the object, of the image, as viewed from those two places. You and I use our two eyes, and our brain is smart enough to combine those views to give us information about how far something is away. But it turns out that we can use exactly the same concept and apply it to astronomy. For example, if we take a pencil and place it in front of our face, and then cover our right eye, we will see an image. And then if we switch and cover your left eye, we see another image. But the apparent location of that pencil is different as viewed from those two locations. As I said, our brain has a way of naturally combining those two images to give us depth perception. Okay, so we don't have to think about it, we just do it. But what's important as we analyze the situation is to recognize that the farther away an object is from us, the less difference its apparent location will be as viewed from our right eye or our left eye. If something is very close, its apparent shift is very large, whereas if something is far away, its apparent shift is very small. And that apparent shift, due to viewing from two different positions, is a concept known as parallax that we're going to talk more about. So when we talk about parallax, this can be a good thing or a bad thing. As long as we know that it's happening, we can use it to our advantage and actually extract information by using that parallax. And so essentially what our job right now, what the job of astronomers is to do, is to use the parallax as we view stars in the sky to our advantage and use their apparent shift as viewed from two different locations in order to determine how far away that star is. So as the title of this slide indicates, nearby stars exhibit parallax. Far away stars, in principle, also exhibit parallax, but if they're too far away, the amount of parallax will be so small that it won't be useful. So it is important to note that while we will be able to use parallax to determine how far a star is away, it'll only work up to a certain distance. So the first question then, if we're going to try to exploit the concept of parallax and use it to our advantage to determine how far away stars are, the question is, where are our two astronomical eyes, right? And what I mean by that is, in order to use stereoscopic vision ourselves, what our brain does without our thinking about it, it takes these two images from our two eyes and says, this object is this far away, as the difference in its apparent location is this big as viewed from your left eye and the right eye, and so it does an internal calculation, says, aha, that object must be 5 meters away. But we don't have astronomical eyes, or if we do, we need to figure out what those are. So how do we view the same star from two different locations? And the answer is, we view it at different places in the Earth's orbit. So this is a schematic, not to scale, because these stars are much farther away than an astronomical unit. But if you look at the Earth during its orbit, you see that today, if this is the location of the Earth today, up at the top of the orbit, 6 months from now, it will be down at the bottom of the orbit. And so if we view the same star today and 6 months from now, and take very careful pictures of those stars, we can compare those pictures, and we actually will see the same star in slightly different locations. So for example, if we make this type of parallactic observation with two stars labeled A and B, if star B is twice as far away from star A, if star B is twice as far away from Earth as is star A, then it will shift only half as much due to the parallax. Because remember, again, the closer something is to us, the larger its apparent shift due to these two different observations. So parallax is larger for nearby objects and smaller for far away objects. And the effect is proportional. So in other words, the degree of parallax is inversely proportional to the distance. So doubling the distance cuts the parallax in half. Halving the distance doubles the parallax. And these measurements of location, they always need to be relative to something. So when we measure the location of a nearby star, we do it with respect to distant background stars, by which we mean stars that are so far away that they don't have any apparent movement. We can't measure their parallax. And so this is the key. We don't have two eyes that are 2 astronomical units apart, but effectively we create those eyes by making observations 6 months apart. So this is the schematic here at the top. Obviously gives us I think helps convey exactly what's happening, but it's also helpful to see what it would look like, what these observations would look like for us here on Earth, because we don't get the top view, right? We just get the view as we see the sky. And so we have the distant background stars here in yellow. So if you look at the view today, the view in 6 months, and then the overlay of those views, the yellow background stars are so far away that they don't exhibit any measurable parallax. And so they're in exactly the same positions today and 6 months from today. But stars A and B, which are relatively nearby in astronomical terms, they do change positions. And you can see in the overlay of these two views that star B moves half as much as star A. And that tells you again that star B is twice as far away as star A. And here is a video or an animation that you can watch on YouTube by following the link. I don't think that it will work actually when I export this video, so I think you'll have to pause me and follow the link or click on the embedded video. But it does a nice job of showing you what the real-time view from Earth would be of the sky and of these stars exhibiting parallax as the Earth moves around in its orbit. So definitely pause me and take a look at this, and hopefully it'll help convey, a little bit better what parallax really does to our view of the sky. So now that we understand the concept of parallax, let's get a little bit more detailed and think about how we actually measure the angle theta here, which is known as the parallactic angle. So this is the basic setup. We're going to make 2 observations of the same star. We've labeled this star a foreground star to distinguish it from the distant background stars. So remember, these distant background stars are so far away that they don't exhibit any measurable parallax. So from our vantage point, they appear just fixed in the sky, whereas this foreground star is near enough that it does exhibit some measurable parallax. So we're going to make observations of this star in June and then in December, 6 months apart, and we're going to observe this. We're going to observe some apparent shift, and we want to relate that to something that we know. So this is the angle, what we call the parallactic angle. So it's half of the entire angular separation here, and we want to measure it. So the key is to look at this shaded triangle here. And for those of you that have taken geometry or trigonometry recently, this will be completely obvious. For those of you that haven't done it so recently, this will just be a fun refresher. So the key is to recognize that the distance between the sun and the Earth in its orbit is 1 astronomical unit, right? So that's a distance that we know. And then there's some unknown distance, d, that is the distance from the sun to this foreground star, right? So we want to relate that to this angle theta. And for small angles in geometry, if you were actually doing this in a trig class, you would actually write down the tangent of theta here. But it turns out that the stars are so far away, so much larger than 1 astronomical unit, that the angle is so small that something called the small angle approximation applies, in which the tangent of theta is approximately equal to theta itself. And if you want to know more about what I just said, please ask either directly or on the class discussion page. If you wish that I hadn't said anything about tangents at all, then just sort of wipe the last 20 seconds of your memory and you'll be no worse for the wear. The upshot is that the distance from the star to the sun, which is essentially the same as from the star to Earth, is related to this parallactic angle in this very simple way. So the distance as measured in a unit called a parsec, which I'll say more about in a second, is equal to 1 over, or 1 divided by, the parallactic angle as measured in arc seconds. And so an arc second turns out is 1/60th of an angular second, which is 1/60th of a degree. Okay, so 1 arc second is 1/3600th of a degree. It's a very small unit of measure, which just goes to show you that these stars that we observe, when we do see parallax, it's a very small effect. So you really have to be very careful when you're taking these pictures. You have to be very careful, that your setup is identical between December and June, for example, or you're just not going to get any measurement at all. But if you do it carefully, you can measure this parallactic angle, and you can use it directly to get the distance as measured in parsecs. A parsec, for what it's worth, is 3.26 light years, which is that's the conversion. There's nothing deep about parsec. It's just a convenient unit that astronomers use. You can use light years, you can use parsecs, but for the parallax equation, it needs to be measured in parsecs, and you need to measure the angle in arc seconds. So just to actually write it down so that you don't have to rewind and listen to me talk again. The arc second, it's a very small unit of measure of angles, and there are 60 arc minutes in a degree, and there are 60 arc seconds in an arc minute. And again, this parsec is, it really is the most common unit of distance in astronomy, at least outside of the solar system. If you're focusing on the solar system, we tend to use astronomical units. But if you're dealing with things beyond the solar system, we tend to use parsecs. Again, it's about 3¼ light years, so you could just as easily use light years, but for historical reasons, parsecs have been settled on. So we'll use both units, but now you know what they are. So the idea of parallax has been around for a long time. People have understood parallax. But of course, the application to astronomy didn't come around until we were all settled on the notion that the Earth actually did orbit, right? If the Earth is at rest in the solar system and in the universe, then there's no such thing as parallax because we're always observing things from the same place. In fact, if we observe stars moving and we think that we're at rest, then the stars really are moving. And then you would have a question, well, why does the star move back and forth, every 6 months, for example? But once we know that, in fact, the Earth is orbiting, then we start to realize, aha, we can use this parallax to our advantage and use it to map the stars in our galaxy. We can start to identify stars that are nearer to us and stars that are farther away. And then, as we mentioned a couple of times, we can finally start to disentangle the brightness effect and figure out, is this star bright because it's close by, or is it bright because it's absurdly luminous? Okay. So the first stellar parallax was measured in 1838. And so, again, the concept had been there. They certainly knew by then, for quite some, over a century anyway, it was more or less settled in the scientific community anyway, that the Earth was orbiting. So the idea of applying parallax to astronomical observations was out there. But as I mentioned, it's a hard thing to do because you really have to have your apparatus and your telescope set up extremely precisely because these, the parallactic angles that you're trying to measure are quite small. So it wasn't until 1838 that scientists were able to first actually measure the stellar parallax. And when they did, they finally got a glimpse into just the sort of mind-bogglingly huge length scales. Going forward a few years, in the 1990s, a relatively recently launched space satellite called Hipparcos observed the parallaxes of 120,000 nearby stars. And of course, nearby is relative, right? But in astronomical terms, these are nearby stars. And so we've gone a long way from measuring the first parallactic stellar parallax in the 1830s to now having a satellite do it automatically and getting over 120,000 nearby stars. The great thing about that, though, is that now astronomers are able to measure the distances to these stars. And Google took one for the team and used this data to construct a 3D map of all of these nearby stars. And so I have the URL here down at the bottom of the page, and I certainly recommend pausing me and giving yourself a rest from the drone of my voice and just kind of poke around there and take a look at what they did. I hope they leave that up, for the rest of eternity, because it's a pretty cool thing, and it's sort of mind-boggling to me that we can actually get that kind of data and do that kind of analysis so routinely now. So I hope you enjoy that. So let's put this into action a little bit now. Consider the following example. So you're going to observe two stars, X and Y, and star X has a parallactic angle of 6 arcseconds. So that means that when you look at its location in June and you look at its location in December, its apparent movement in the sky is the angle between those two locations in the sky is 6 arcseconds. So not a big parallactic angle, but you're able to measure that. Star Y has a parallactic angle of 2 arcseconds. So the question is, which one is farther away and by how much? So I'm going to pause here for my usual 30 seconds or so. If you want to ponder it longer, you are, as always, welcome to pause me. If you want to skip the silence because you know the answer immediately, you certainly have the power to do that as well. So think about this for a little bit, and then we'll come back and discuss it. Okay, so I'm going to spoil it now, so if you want to think longer and harder, pause me now. So the key here is to remember the parallactic equation, which is that the distance from us to the star is inversely related to the parallactic angle. So d equals 1 over theta. And so in this case, star X has 3 times greater parallactic angle, which means it is 1/3 the distance of star Y. Because remember, larger parallactic angles mean closer stars, and smaller parallactic angles mean farther away stars. So since 6 is 3 times larger than 2, that means that star Y is 3 times farther away, or star X is 3 times closer. So the answer is A. Okay, so now that we've sort of beaten parallax into a dead horse, we can finally start to do what I promised you, which is that we can start to disentangle this complicated brightness relationship and its dependence on both luminosity and distance. So brightness is also known to physicists as intensity. So it's a measure of how much energy do you have per square centimeter or per square meter per second coming to you from a star. And the relationship between the intensity and the luminosity and the distance is captured in this equation, which you've seen before, but it's been a little while, so we'll throw it back up here. And all it does, you may or may not love math, but all it does is it says, well, the luminosity is the total energy emitted per second, right? It's the power of the star. So it's sending out in all directions equally some amount of energy per second. As that light travels out, it creates larger and larger spheres over which that energy is distributed. And so since energy is conserved, once the energy is sort of emitted, you're not getting more or less energy in that sphere. The sphere is just getting bigger. So the luminosity is the total energy emitted. 4 pi r squared is the surface area of the sphere over which that energy is now distributed. And so the intensity is just equal to that total luminosity divided by the surface area. And so this is the reason that the brightness, which is what we observe, we measure the intensity of the light that gets to us. And so we aren't able to measure the luminosity by itself We only get the luminosity divided by 4 pi r squared. But the key is that using parallax, we're now able to get a separate measurement of the distance. And so now that we know, if we know the distance and we know the brightness, we can actually calculate the luminosity of the star. And that's what's summarized here in this slide. And so mathematically, we're just solving the equation on the previous slide for the luminosity, because we're able to measure the intensity of the star's light that arrives on Earth. We can then use parallax, assuming that the star is close enough that it does have a measurable parallactic angle. We can use parallax to measure the star's distance from the Earth, and then finally we can combine those to calculate the intensity or the brightness of the star. So, and I think I've mentioned this before, but just to remind you, luminosity is measured in watts. In principle, luminosity is measured in watts. And I say in principle because stars are so extraordinarily luminous that when you measure it in watts, the number is enormous. So the luminosity of the sun, for example, is 3.9 times 10 to the 26 watts. So that's, 39 and then 25 zeros after it. So you get tired writing that down. Scientific notation saves you. But as a matter of fact, very often when we write down the luminosity of a star, we just express the star's luminosity in units of the sun's luminosity. So we might say it's 5 times the sun's luminosity, or half the sun's luminosity, for example. Makes it a lot more convenient than writing out huge numbers. So, for example, a star might be 100 times brighter than the sun, and then we could write the star's luminosity is 100 times the sun's luminosity. Or the star is 1,000 times fainter than the sun, and using scientific notation, we could write that the luminosity of a star is equal to 10 to the minus 3, which is 1,000 times the luminosity of the sun. So let's look at another example. You're observing 2 stars, and star A is 10 times as luminous as the sun, so you know that somehow. And the sun is 100 times as luminous as star B. So star A is 10 times as luminous as the sun, and the sun is 100 times as luminous as star B. Moreover, star B is 200 times closer to the Earth than star A. That's a lot of numbers. Which star appears brighter to an observer on Earth? Okay. Now, as always, you're welcome to pause me here. I actually won't pause because I think it'll be more valuable, probably just to talk through the solution, how we would solve this. But if you want to give it a go yourself before I ruin it for you, by all means pause and knock yourself out. I'll be here when you get back. Now, for those of you who were disappointed every time that I told you this wasn't a class in advanced mathematics, here is probably the most math that you'll see all semester, so enjoy it while it lasts. The key to answering this question is just to write down the relationship between the intensity of each star's light and its luminosity and distance, right? So, for example, star A's brightness or intensity is equal to its luminosity, LA, divided by the surface area of that sphere, again, 4 pi RA squared, where RA is the distance from us to star A. And the same relationship holds for star B. So the key now is to divide these two expressions, because we're trying to figure out, well, which star is brighter, right? So we want to know, how do the intensities compare? So we're going to divide the intensity of star B by the intensity of star A. And when we do that, after just a little bit of algebra, we can cancel out the factors of 4 pi. And we find that the ratio of the intensities is equal to the ratio of the luminosities times the square of the inverse ratio of the distances. Okay, so that was a lot of words, but the important thing is that the ratio of these luminosities, LB over LA, is in the same order, if you will, as the ratio IB to IA. In contrast, you'll notice that RA is on top and RB is on the bottom here. And basically, that's just a way of quantifying, of seeing mathematically the fact that if a star is farther away, it's definitely going to be less bright than it would if it were closer, right? So the intensity, you know, as a star's intensity goes up, its luminosity goes up. But as the intensity goes up, a star tends to be closer as well. So I hope that didn't confuse it more than it helped. It's just math as well, and as always, if you want to talk more about it, you certainly can. But you followed through the math, and now we're ready to plug in. We know that the luminosity of star B is 1/100th the sun's luminosity, and similarly, star A is 10 times as luminous as the sun. So we plug those things in. Finally, we know that star B is 200 times closer to Earth than is star A, which means that RA over RB is 200. You plug those numbers in, and you find out the answer is 40. So in other words, IB divided by IA is 40. So star B appears 40 times as bright as star A. So if this were a physics class, we would do a lot more calculations like this. We are not going to do a bunch of calculations like this, but I wanted to show you at least one example of a real calculation, so you can kind of get at least a sense of how these things are actually done. And I'm glad to say that that is the end of this lecture. So this was a short one. I hope that there wasn't too much pain packed into there by virtue of the math that we just did, for example. So we're going to wrap it up there. We're going to have a couple more lectures on analyzing starlight. So this is just the very first one. But I hope that you're enjoying the transition as we go from building up the wealth of knowledge that we have over the first 9 lectures, and then here in lecture 10, finally taking the next step and starting to extract some information, figure out how can we actually measure how far away these stars are, and then and how can we disentangle again this relationship between intensity, luminosity, and brightness. So we'll continue to use these concepts going forward. So thanks for your attention today, and I'll see you back here for lecture 11.